So in this class we are going to discuss the details about the Poisson's equations or Laplace equations, right? This you can consider as the conclusive part of the syllabus that we have in electrostatics. So let us go directly and see what are the Poisson's and Laplace equations are and what are the significance of these expressions, right? So first we will try to relate the intensity of E field with the electric potential. So we are going to find out the expression for Poisson's equation first, and after that we are going to apply the expression for Poisson equation to get the Laplace equations, right? So to start with, let us start with here the intensity of E field E and electric potential V at any point in an electric field. Okay, you can write in an electric field if field are related as or related by the expression E is equals to minus grad V, that is gradient of V. So we can write from here E equal to minus del V. Since we are talking about gradient here, no del and dot or cross is appearing. So this is, let us take our expression number 1, right? Now also we know that this del, or you can write here, I believe that you know that we have already discussed in your previous classes that del is actually defined as ax del x plus ay del y plus az del z, right? So this was the expression for del operator. Now for a continuous or for continuous distribution of charge of volume charge density rho, that is rho is the volume charge density, you know that. Differential form of Gauss law will be del dot E is equals to rho by epsilon naught, right? So this is, let us take this as our equation number 2. So from these two equations, so we can write from equation number 1 and equation number 2, we can write, we'll simply put the value of E here. So del dot minus del V is equals to rho by epsilon naught. So I'm just putting the value minus del V from here, from equation number 1. So here, or we can write del dot del V is equals to minus rho by epsilon naught, right? So we consider this as our equation number 2. Now del dot del, suppose let us find out what is the value of this del dot del, right? So now del dot del is equals to, del is this ax dx del x. So we can write the value, the expression for del operator, ax del x del x plus ay del y plus az del z dot of ax same del lx plus ay del y plus az del z. So this is the expression for del dot del. So we can consider this as del square del x2 or del 2 del x2 plus del 2 del y2 plus del 2 plus del z2, that is equals to del square, right? So here this del square, remember this del square is actually known as this Laplacian operator. We have discussed about this in our earlier classes also. So this del square is known as Laplacian operator, right? Now, so what is the expression that we finally coming from here? After this, I'm just, a small part is left, so I'm using this part of the board. So from here we can say now del square, so this del dot del minus del V, from here I can write this is equals to del square V is equals to minus rho by epsilon naught. So this is our equation number 4. Okay, so this equation is actually our equation of Poisson's, or there was, I mean, the person named Poisson. Actually, the pronunciation is Poisson. So this is the expression of Poisson equation, and in MK system, in all any other system at Wilson, you can use this one. So what is the significance of this Poisson system is that it relates charge density to second derivative of potential V, right? I'm also repeating again, just try to remember this one. What is the purpose of using this Poisson equation? What is the significance? Significance is that it relates charge density to second derivative of potential V, right? So after this, let us see what is the expression of Laplace equations, right? So let us see now what is about this Poisson equations. So remember that previously that I mean Laplace equation we will see now. So remember the Poisson equation that we had earlier. So that is del square V is equals to minus rho by epsilon naught, right? So that was the case that we had earlier, right? So now to evaluate the or to see the details about the Laplace equations, let us now start this discussion, right? So in region where there is no charge, that means we are considering a region where there is no charge is present, or where volume charge density is 0, that is rho equals to 0. So that means we are considering a region where there is no charge is present there, and if you know that if there is no charge present in that particular region, so we can say that the volume charge density rho is equals to 0 in that particular region. So now thus by substituting rho equals to 0 in our Poisson equations, so we just put the value of rho equal to 0. So what we have? So this we have del square V is equals to 0. So this is your Laplace equations. So simple thing is that you have the Poisson equation. Now you put the value of rho equals to 0. That means you consider if the same thing that we have discussed in the Poisson equation, if we consider this, only the difference is here we consider that there is no charge is present, or the volume charge density rho equals to 0. So in that case we put the value of rho equals to 0, and whatever the expression comes, this is your Laplace equation, right? So we can also have this expression for Laplace equation in 1D, 2D, 3D forms. So let us write a few. So this Laplace equation, so I am writing in short LE in 1D form is expressed as del square V is equals to del square V del x2 equals to 0. This is the 1D form. If you just remember this form, sometimes it appears that questions used to come, some problems used to come. So you just, if you remember this expression first, you can directly solve those problems very quickly. So its solution is in form given by the solution of this expression. If you solve this differential expression or partial differential equations, so I believe that you have done in your engineering mathematics course, so that will be coming equals to v equal to mx plus a, right? Now in, let us see another one. So Laplace equation in 2D form. So in 2D form we will have del square v plus del square v is equals to del 2v del x2 plus del 2v del y2, that is equals to 0, and its solution will be coming as v of xy. See, in 2D form we will have two different variables here, x and y, so that will be equal to 1 by 2 pi r v d v d l. So this is a line integral, right, where it depends on the, I mean if it is a closed surface, we are if there is surface like this, so we will have the closed surface like this, so you can put a circle sign, that means a closed line integral sign also you can use. That depends on the surface of our concern, right? So where this r equals to the radius of a circle about point about point xy. So about this radius of the circle, about a point, that point is represented by xy. So it's a variable, you can have it, use any value. So another one, let us see also the last one. In Laplace equation in 3D form, we can represent it del square v is equals to del 2v, just simple three terms will be there, del 2v del x2 plus del 2v del y2 plus del 2v del z2 equals to 0. Equals to 0 is because Laplace equation, the right hand side is 0 always, so this is also equals to 0. And so if we, the value of v actually at any point p is the average value of v over a spherical surface of radius r centered at p, and it is given by, that means we are talking about the value of v, is this v we are talking about. So this value of v at any point p, say any point you can consider at any point p, is the average value of v over a spherical surface of radius r. If you have a spherical surface and the radius is denoted by r, so value of v at any point p is the average value of v over the spherical surface that I have just drawn of radius r centered at p. So centered at p, so this will be the p, and it is given by the solution v of p will be equals to 1 by 4 pi r square integral of v ds, right? So this will be the solution. Now Laplace equation, what is the significance? Let us also discuss the significance of this Laplace equation. You just remember a very simple thing, that Laplace equation is used to find the potential in a charge free space. So what is the significance of Laplace equations? So you can simply write Laplace equation is used to find the potential in a charge free space, that is where there is no charge is present. So as simple, this is the significance of Laplace equation, right? So once we have this discussion related to the Poissons and the Laplace equations, it is now important to see the details of this uniqueness theorem. So this is uniqueness theorem. So as per the theorem, you can also find in the book, I'm telling it also again. So as per the uniqueness theorem, a potential function which is a solution of Laplace or Poisson equation, that means we are talking about the solution. Just I described the 1D Laplace equation, 2D Laplace equation, 3D Laplace equations. So what it means, that the potential function which is a solution of Laplace or Poisson equation satisfies the boundary condition, which satisfies the boundary condition is the only solution. That means Laplace equations or Poisson equation can have only one solutions. So let us write it for your sake. So it says, as per this uniqueness theorem, a potential function which is a solution of Laplace or Poisson equation and satisfied, and potential function which or Poisson equation and satisfies the boundary conditions. That means it also should satisfy the boundary conditions, is the only solution, right? Or in brief, actually you can say that the solution so obtained is unique. That means only one solution can be present. Or you may write the solution so obtained or obtained by this, using this Laplace or Poisson expressions, obtained is unique. That is, can have only one solution, right? So this is the uniqueness theorem. Now let us see that whether this is true or not, right? So I'm just making some space, I'm omitting this theorem part. So now we will see whether this is true or not. It should be having only one solution. Let us see whether it is true or not. So first to see whether it has only one solution, let us consider that it has two solutions, right? Now if we can prove that there cannot be two solutions, or these two solutions which I am at the start I am taking, there are two solutions. If we can prove that these two solutions are equal, then only we can conclude that if these two solutions are equal, that means only one solution is present, right? So we are doing that. So we assume that first, that there are two solutions, v1 and v2 of Laplace equations. But see, as the uniqueness theorem tells, there cannot be two solutions. But for the sake of our understanding, I am taking that v1 and v2, let us these two solutions are there. Now if we can equate this v1 equals to v2, we simply said both are same, that means only one solution is there, right? This is our process or way of proving the uniqueness theorem, right? So of Laplace equation, both of which satisfy the prescribed boundary conditions, right? So thus can say that del square v1 equals to 0 if v1 is one of the solutions. Del square v equals to 0 is the Laplace equations we have just discussed. So we are considering del square v1 equals to 0 and also del square v2 equals to 0, right? So let us take as equation 1a, right? And also we consider, since we are satisfying the boundary condition, at the boundary conditions, satisfying boundary conditions means we are considering this v1 equal to v2 on boundary. I mean, for the sake of our discussion, since we are taking at the boundary conditions, that satisfying the boundary conditions, so we are taking v1 and v2 only at boundary. Now at last, when we will prove that this v1 should be equal to v2 in all places, I mean not only in the boundary but everywhere. But to start our discussion, I am taking this v1 and v2 is equals to v2 just at the boundary, right? So we take it as our expression 1b, right? Now we consider the difference vd equals to v2 minus v1. So let us take as equation 2, right? This is the expression between v1 and v2. Since v1 equals to v2, I can write that v2 vd is the difference between v2 and v1 at the boundary, right? Which obeys del square vd. Just I am using this del square here. So del square vd will be equal to del square v2 minus del square v1. That is equals to 0. So let us take as equation number 3 here. What I have done here, just I have taken the del square in both right hand side, left hand side and right hand side. So this comes, so we consider this as equation 3a, and vd is equals to 0 on boundary or at boundary, you can, whatever you can say. So let us take that equation 3b, right? Now as per equation 1, from we will apply divergence theorem at equation 1. So as per equation 1 from divergence theorem, I'm talking about Gauss divergence theorem that we have already studied in our previous classes. So you can write this volume integral of del dot a dv is equals to closed surface integral of a ds, right? So we take this as expression number 4. Now let a is vd del vd and use a vector identity. What is the vector identity? Del dot a is equal to del dot vd del vd del vd, that is equals to vd del square vd plus del vd, right? Okay, so now I'm omitting, I have to omit the screen, so you can go back and up to this you can check, right? So remember these equations. Now, so we have got this expression of del A, so we can write, but we know that del square Vd is equals to 0. So therefore we can write del dot A is equal to del Vd dot del Vd. Let us take as our equation number 5, right? Now substituting the value of this equation number 5 into the previous expression, that is our equation number 4. So we will just substituting 5, equation number 5 into 4. So what comes? Volume integral of del Vd dot del Vd dv is equals to closed surface integral of Vd del Vd ds. So let us take as equation number 6, right? So now from 1 and 3, equation number 3, it is evident, or it is proved that RHS of equation number 6 vanishes, right? So you can see equation number 1 and 2, right? So our right hand side vanishes. Hence we can write volume integral of del Vd square dv is equals to 0, right? So from here, since the integration can always be positive only, so the integration is always positive, so we can write del Vd is, integration is always positive, we can write this del Vd equals to 0, and we are considering it as our equation 7a, right? So, or from here, if this del Vd is equals to 0, as you can remember Vd in the previous expressions, we have got Vd equals to V2 minus V1. So from here we can write, or Vd equals to V2 minus V1 equals to constant everywhere, right? Since del Vd equals to 0, and so we can write that this Vd is equals to V2 minus V1, which we know we have discussed previously. So this Vd equals to V2 minus V1 is constant everywhere. So let us take as equation 8b or 7b. Wait. So we take this as our equation number 7b, right? Hence we can conclude that Vd is equals to 0, or V1 is equals to V2 everywhere. So that means if V1 is equals to 0 everywhere, so when we started the discussion we have talked about this V1 and V2 is equal only at the boundary, but here we have proved that V1 is equals to V2 everywhere. So we can conclude that V1 and V2 cannot be different solutions of same problems. So they cannot be different, that means they are same. So our uniqueness theorem is proved here. That means for uniqueness theorem, the solution, there is only one unique solution can be there in case of a Laplace or a Poisson equation, right? So this is the proof.